So yesterday we started talking about scheduling problems. The basic problem is if you have more than one process to choose from, which one should I choose first? Which one should I run next? And how do I make this decision? That's the scheduling problem. We talked about the basic problem and we said that there is no single answer to this problem. O ne ya artık 22'den başlıyorum biraz 22'de yok ha. We said that there is no single answer to these questions. We said that it is dependent on the type of the operating system that we have and type of the environment that we have. But at some point, if you have more than one process to run, at some point you have to decide which process should run next. And these are the points where we should make this decision. After we make a new process, when a process exits, it terminates. We need to make a decision which one to run next. When a process blocks, what do I do now? And when an I/O completes and it causes an interrupt, I make to have that decision again. And finally, if I have a timer interrupt, then I should make that decision which one to run next. And we talked about this preemption versus non-preemption concept. It is an important concept. It defines two types of operating system. One lets the processes run until they are done or until they are blocked. The other one says that no, there is only a limited time available for each process, and each process should not run more than that amount of time. Okay, these were the things that we talked about last time, and we were talking about the goals. How do we make this decision? It depends on the goals. Okay, the goal of the operating system or the goal of the scheduling subpart of the system is all of the schedulers should be fair. Okay, these are the common goals. It should enforce the policies and it should keep a balanced system. That means that all parts of the system should be kept busy. These were all the common goals. But if we go specific, for example, for the batch systems, they try to maximize throughput. What is throughput? Throughput is
bir saat içinde yaptığı iş sayısı.
Saat başına yapılan iş. So the jobs per hour. How many jobs did you complete per hour? That's the throughput. This should be high for the batch systems. And turnaround time should be smaller because when I submit a job, it should be done quickly as possible, and CPU utilization should be high. These are for the batch systems. But when I come to other systems like the interactive systems or the mobile systems, these goals are not very good goals for me because I don't want my CPU utilized 100% of the time on my cell phone, because if I do that, my battery will be consumed in an hour, okay? Or my cell phone will not last for more than 2 months maybe if I keep using it at 100% CPU utilization. So these goals are common to all systems, okay? Fairness, policy, and enforcement and balance. However, these are only specific to batch systems. How about interactive systems? Yes?
What about one job? It's one cycle or one instruction? What is it?
And we talked about this yesterday. For the batch systems, one job is a complete job of calculating the payroll numbers for the whole government workers. Or for a bank, calculating the interest rates for the 2 million customers. So these are the jobs, types of jobs that we're talking about. Since these are batch systems, what's a batch system? These are for mainframes actually. You don't have a batch system on a PC. For a mainframe, you need to complete the balances of all the customers for 2 million customers of a very large bank, okay? Or the payroll calculations of the government workers. So it takes lots of time to calculate all of those. Those are very simple calculations, but it takes lots of time. So you submit your job, okay? Your job should be done in an hour or 2 hours or 3 hours, sometimes the whole day, okay? So these are big jobs. These are not like word processing jobs or the special jobs. These are straightforward, repetitive, but large jobs. Okay. So for the interactive systems, we said that response time is the priority. We don't talk about CPU utilization. We say that response time should be as small as possible, so that the user can feel the user can feel that the system is always responsive. And we talked about this concept of cheap and expensive requests, and these are important distinctions. To define these cheap and expensive requests, we need to talk about human psychology. Since these are used by the humans, human-computer interaction thing is going on here. There are some psychological issues that we need to be aware of. So, even though we are talking about computer science and operating system, human psychology plays some role in this case. Okay, for the real-time systems, we don't talk about response times. We talk about meeting the deadlines and predictability. Okay, these are the main goals when we are designing schedulers for these types of systems. Okay, so let's go back to batch schedulers and talk about what kind of schedulers we can have. Remember, for the batch schedulers, what we said was, o çekiyor mu ya?
Evet hocam.
Geliyor değil mi? What we said was, throughput is important, turnaround time is important, and CPU utilization is important. Okay? So, to maximize those, to meet those goals, we have these 3 batch schedulers. First come, first served, which is the simplest one. Then the shortest job first. Then the shortest remaining time first. Okay. Let's look at these. Let's look at these schedulers one by one. The first come, first served. If you have many jobs, let's say job 0, 1, 2, 3, and 4. Each one can take maybe 1 hour, 2 hours, 1.5 hours, those kind of stuff. The scheduler says that first process it runs the first process first. Whatever comes first will be run first. Okay, so it is as simple as this. So this is the simplest scheduler that we can have. We cannot have any simpler scheduler than this. The simplest scheduler than this would be no scheduling at all. That means I am not running a multitasking, multi-program system. Okay, so this is the simplest that you can have. The rule is the first come, first served. Whoever comes first will be run first. When the running process blocks, okay, if it's blocking, then the first process on the queue is run next. So I am trying to keep. What was our goal? Throughput must be high, turnaround time must be low, and the CPU utilization should be high. So the second one, when the running process blocks, the first process on the queue is run next. Because I need to keep CPU busy. Okay? And never preempt based on timer. Why? You don't do any preemption with the batch systems. Why?
Hocam preemption yapınca zaten sıra sistemini bozmuyor mu? O zaman
Block olduğu zaman da bozuyor.
Ama blok olduğunda ondan sonraki ilkini alıyor, tekrar şey koyuyor. İşleme koyuyor.
Sonuncusu geldiği zaman yani birincisi Q'da beklerken sonuncusu çalışıyorlar mı? Oluyor. Birincisi block oldu, ikincisini çalışmaya başladım. Birincisi çalışabilir durumda bekliyor. Fasilite ama hala ikincisi çalışıyor değil mi? Dolayısıyla her zaman birincisi ilk geldiği için başlıyor ama block olduğu zaman ikincisi devam ediyor. Birincisi sırada bekledi yani. Aynısını timer'la da yapabilirlerdi. Biraz öbürü içerisinde falan diyebilirler. Niye yapmamışlar? İkincisini niye yapmışlar?
Hocam bu şeyden olabilir mi? Normalde mikrostik yok. Timer kullansak, bir switch falan yapsak çok o zaman şey olmuyor, yüksek olmuyor.
Niye?
Hocam çünkü hani o an çalışanı timer'a bağlı olarak şey blokluyor.
İkincisi de blokluyor. İkincisini niye yapmışlar? İkincisi niye var orada? End running block yani şimdi first come first server'ın şeyi arkadaş da söyledi orada. İlk gelen ilk önce işini bitirsin, işini bitince ikinci çalışmaya başlasın. Öyle yapmamışlar ama. İlk gelen blok olduğu zaman ikincisini çalıştırıyor.
CPU'nun tamamen çalışmasını sağlıyor.
Evet, amaçlarımızdan bir tanesi neydi? CPU utilization. O yüzden yapmış ikincisi. Üçüncüsü niye yapılmamış peki? Niye preemption kurulmamış? Üçüncüsünü yaptığımız zaman ne oluyor? Preemption ne işe yarıyor? Preemption ne işe yarıyor?
Hepsini eşit. Daha önemli olan proses işliyor.
Bütün proseslere
Daha
eşit
kısa
süre
olan
veriyor çalışması için.
Bütün proseslere
Yani çalışması için bir süre veriliyor. O süre bitince bir sonrakine geçiyor.
işte niye yapılıyor?
Eşit öncelik vermesi için. Yani hepsi eşit çalışsın diye.
Priority'lerin aynı kalması için diyebiliriz ama base sistemde priority diye bir şey yok zaten. Base sistemde ne var? First come first serve var. Ama diyelim ki elinde preemption olsun. Preemption'da kullanabilirim ama base sistemde preemption'ı kullanmıyorlar. Hani ellerinde olsa bile, tamam mı? Kullanmıyor. Kullanmamamız lazım diyor. Niye öyle?
Hocam dün demedik mi realtime sistemler belli bir şey?
Bir dün dediklerimi bir hatırlasanız zaten bitireceğiz. Ben dün demedik mi zaten demedim. Dün söyledim.
Realtime sistemler belli bir işi belli bir sürede halletmeye garantisi veriyor ya. O işi halletme garantisi için bloklanamıyor.
Hayır o real time sistemi. Dün söylediğimizi karıştırıyorsan real time sistemi. Real time sistemler öyle. Real time sistemde preemption'e gerek yok.
Bu batch.
Bu batch. Evet. Batch sistemlerde tamam mı? Real time yapılmaz. Preemption yapılmaz. Kural. Kötü bir şey. Evet.
Hocam çünkü prosesler arasında geçiş yaparken CPU boş kalıyor ve hani o ağır çalışmıyor. Ve burada okuma yapmak.
CPU boş kalmıyor da CPU context switch yapmak için falan kullanıyorsun. Zaman kaybediyorsun. Doğru zaman O zaman niye preemption diye bir şey var? Madem kötü bir şey.
User interaction sağlamıyor. Yani bizim batch sistemlerde user interaktif değil ama diğer sistemlerde user interaction sağlamak
Evet.
için preemption kullanılıyor.
Batch sistemlerin user interaction'la alakası yok. Dolayısıyla her bir prosese küçük eşit zamanlar verir ki her biri de interaktif kalsın, responsive kalsın diye bir şey yok. One of the batch jobs might be calculating all the digits of the number pi. The other batch job might be calculating the payrolls of a government workers. Okay, so I don't need any interaction. So preemption is something expensive. You are wasting maybe 10% of your time for context switching and doing that kind of stuff. So it has some cost. If you don't need preemption, if you don't need this kind of behavior, then don't do it because you will lose some CPU time. Since one of our goals in the batch systems is to maximize CPU utilization, then I don't use preemption in this case. Never preempt based on timing. Okay. It is very simple to implement, just like waiting in line. Okay. When you get your turn, you use your CPU, and it is not very fair. Okay. No preemption means that CPU-bound processes take more CPU priority. Right. That's what we said actually. So it is not very fair. So one of our common goals was to be fair, but in this case it is not that fair. But in this case, as I said, to be fair is not, as long as my job is done in a day or something like that, it should be okay. Because if you do no preemption, and if I have a CPU bound process like the scientific calculation without doing any input output, then in that case that process will take the CPU and will use the CPU 100% of the time for a very long time. So other I/O bound jobs will not take any CPU time. So fairness is kind of not satisfied with this kind of system, but we don't have to be fair in a batch system actually. Okay, so any questions on this one? Very simple system. Just let the process run until it clocks. Let it clock to the switching, but never create based on memory. It's important. Okay, so this is first come first serve. Again, we are talking about batch schedule, first come first serve. Then we will talk about shortest first and shortest remaining time first. Shortest first is less. What do I mean by shortest first? Let's say I have four jobs, job A, B, C, and D. I know that job A will take 8 minutes to run, job B will take 4 minutes to run, C will take 4, and D will take 4. How do I know that these jobs will take this many seconds or this many minutes to run? Without running them, I wouldn't know how many minutes they are going to take. Right? How do I know that?
Hocam sadece bir iş yapıyoruz. Hani herhangi bir interaction da yok. Böyle olduğu için sistemin şeyine bağlı, özelliklerine bağlı.
So how do you know when you write a program? How do you know how long it will take? You wrote programs, right? How do you? When I write a program, I don't know how many minutes it's going to take. I just run it and see. How do they know that job A will take 8 minutes? Yes.
These kinds of jobs are done every day, and it's an experience.
Yes, it's due to the experience, right? Because as I said, these are straightforward jobs. It is not original job. It is not leave inventions. I know that calculating the balances of all the customers for 2 million customers on a bank will take 5 hours because I did it 2 days ago. I did it last month. I did it 15 days ago. So I know approximately how many minutes or how many hours each job will take. Okay. Suppose you know the time requirements of each job, and this is an example. No preemption. Again, since this is a job batch system, we don't do preemption. Preemption is a waste of time if you don't have any interaction. So this shortest first says that run these jobs first, B, C, and D. Run this one last. What are we trying to optimize here? Remember, we have 3 things: throughput, turnaround time, and the CPU utilization. CPU utilization is okay because I am using this blocking and switching thing. I am 100% utilizing the CPU. And throughput is how many jobs you are gonna do in a given time. So I cannot do better than 4 jobs in 20 hours, right? I will do 4 jobs in 20 hours in this case. I cannot do better than that because this one takes 4 hours, 12 hours, and 8 hours, 20 hours for all of them. So I will do 4 jobs per 12 hours. How about the turnaround time? What is the turnaround time? Turnaround time is how much it's going to take for each job to complete on the average. On the average, right? How much time is going to take for each job? So it says that. So this is the calculation. If I run A first, okay. If I run A first, that will be this will be okay. If I run A first, then B, then C, then D, okay? So how long it would take for D to complete? D will take how many hours?
A plus B plus C plus D.
So, okay, it is 20 hours. it will take 20 hours to complete the job of D. How about C? C will take 8 plus 4 plus 4, 16. And the other one will take 12 and A will take 8. So if I add them up and divide them by 4, okay, this will be my average turnaround time. Okay, this will be my average turnaround time. If I do this order A, B, C, D, and A, B, C, D in that order. So my calculation is something like 4 times A, because for each of those jobs I need to wait for the A. For 3 of these jobs I need to wait for B. For 2 of those jobs I need to wait for C, and for just one of those jobs I need to wait for D. So if I do this calculation and divide by 4, that will be my turnaround time. In this case, shortest first says that, okay, make this A smaller than B, than C. D must be the largest number, right? If I wanted to make this number small, since A is multiplied by 4, B is multiplied by 3, C is multiplied by 2, and D is multiplied by 1. So A should be the smallest. That's why it says that do the shortest first. If you do the shortest first, then you have the best turnaround time. Okay? You have the best turnaround time. In that case, what's that number? Calculate that number.
14.
14?
Yes.
So it is 14. So for this one, turnaround time is 14. How about this one? This will be, let's do the calculation again. Let's do the calculation again. To finish A, it will take 20 hours, right?
10.5.
And for D, it is 12. For C, 8. And how about this one? This is 11. So the turnaround time for this one is 14 and for this one it is 11. So shortest first is trying to optimize the turnaround time. And it is provable fair, it says. I can prove that we cannot do better than that. I know that I cannot do better than, I know that I cannot do better than total of 20 hours. So that will be my throughput. In 20 hours I will be done with all of those jobs. I know that. I am utilizing my CPU 100% of the time. And in order to maximize the turnaround time, I use the shortest first example. Okay? Any questions?
Hocam, burada kısa olan süreleri öncelik verirken mesela
Öncelikli öne alıyoruz.
öne alırken ikisi de aynı süredeyse nasıl karar veriyor? Yani B'nin C'nin önünde olacağını.
Önce nasıl karar verdik? Nasıl karar verdik sence? Tamam değil ayrı. First come first serve. Önce hangisi geldiyse o. Ama hani burada hangisinin önce çalışacağı benim şeyimi değiştirmiyor. Turnaround time'ımı değiştirmiyor. Yani B'de C'nin yerini değiştir. Bu rakam kaç çıkacak? 11. Benim için önemli olan burada fairness diye bir şey yok. Ya değil ayıp oldu ya falan filan diye bir şey yok. Amacım ne burada? Throughput'u, turnaround time'ı ve CPU utilization'ı en iyi seviyede tutmak. Fairness diye bir şey yok. Zaten first come first served'ın şu first come first served'ın şeyi ne? Felsefesi ne? İlk gelen ya önceliktir ya önce yapalım falan filan değil, hayır. Basit olması. Bundan daha basitini yapamazdım o. Basit olması, bundan daha basitini yapamazdım. Okay, so this is my second algorithm for batch schedulers. How about the last one? Before going to the last one, that is the shortest remaining time next, let's look at this issue. This one assumes that at the beginning I have all of those 4 jobs available, okay? At the beginning, somebody told that you have 4 jobs to run in the next 20 hours, and these are your jobs, and choose whatever you want to choose, okay? That will not be the case in the real life, because you know that jobs don't arrive at the same time all the time. I receive a job, okay? Since I have a single job only, and CPU is waiting for nothing, then I will immediately start running that job. While that job is running, then I may have other jobs to run. In that case, we would run into this problem of jobs arriving while the other jobs are running. Okay, so optimality requires simultaneous availability. If all of the jobs are not at the same time, then my optimality, my calculations are here are not valid anymore. Okay, we can't make optimal scheduling decisions without complete knowledge. Okay, without complete knowledge. If I know the job coming order and their times, I can make some optimal decisions. But let's say these are my jobs. Okay, job A will take 2 hours, 4 hours. 1 hour, and then 1 hour. There are a total of 5 jobs I have here, and they will arrive at times 0, 0, time 0, time 0, time 3, time 3, and time 3. So when these two arrive at time 0, okay, shortest first will run the job A. It will start running, okay, and when it is done, job B will start running. And at that time, after job B started running, I will receive this job C because it will arrive at time 3, okay? So, I cannot do anything now. I cannot do anything now because I am still running this job for, and if it doesn't block, then it will continue, okay? I don't know what jobs I will have at the beginning, okay? I only know when they come, okay? So if I do the shortest first run, okay, I will have to do A, B, C, D, E, and my average wait time or my average turnaround time will be 4.6 seconds if these are in seconds, okay? But if I knew that at the beginning, these will be the jobs, okay, these will be the jobs, and they are all available at the beginning, then I would do the shortest first. I would do B, C, D, E, and A. And in that case, it will take 4.4 seconds for the turnaround time. Why do I start with a B, even though it will take longer than A? Because I know that at time 3 I will receive this process C, okay, and it will take only 1 second to complete. So if I do the process B, it will take 4 seconds. Then I can do this B, C, D, E. Each one will take only 1 second. After I am done with those, I can run the process A. So this 4.4 hours or seconds is smaller than this one, so this is one better. But this one knows what kind of jobs I will have in the future. It knows all the information. Okay? Understand this one? So the optimality requires simultaneous availability. Optimality requires complete knowledge of what is going to come. And this one is not that unrealistic. This example is not that unrealistic because in the batch systems, I actually know what kind of jobs I will receive. Okay, what kind of jobs I will receive. Usually these systems are very large systems, mainframes, and they are shared by many customers. And those customers make reservations to use your computer, okay? So you can schedule your customers with these arrival times. You can say that, okay, these are not the arrival times, these are scheduling times for your customers. If you do your scheduling that way, you can maximize your throughput and turnaround time. Okay. So even though it is a very simple scheduling mechanism, if you have this time availability information, It might get a little bit more complicated but more efficient. Any questions on this?
Hocam orada sıfır nasıl oluyor?
Sıfır demek 0. saniyede geliyor.
Yani başta mı geliyor?
Evet. At times diyor ya, arrive at times. 0, 0. Arrive at times 0, 0. Bu 3. saniyede geliyor, 3. saniyede geliyor. Şu 0. saniyede geliyor. Bu da 0'da geliyor. Bu 3, 3, 3'te geliyor. Eğer başlangıçta böyle olacağını bilirsem ben, o zaman üçkağıtçılık yapıp ne yaparım? İlk önce B'yi çalıştırırım, tamam mı? Sonra bunu, sonra bunu, sonra bunu, sonra bunu çalıştırırım. Böyle yaptığım zaman 4.4 saniyeye düşüyor şey. Benim turnaround time. Ama bilmiyorsam böyle olacağını, tamam mı? Elinde 0. saniyede sadece 2 ile 4 var. Ne yapacağım o zaman? 2'yi çalışır diyeceğim. Ondan sonra 2'yi çalışır diyeceğim. 2 bitince elimde 4 kaldı, 4'ü çalışır diyeceğim. Preemption'da olmadığı için 4 çalışmaya devam edecek ama 4 çalışırken 1 saniye içerisinde 3 tane daha cevap geldi. 3'ü de 1. 4'ü kesip onları başlatmam güzel olur ama preemption yok burada. Adam çalışmaya devam ediyor 3 saniye boyunca. 3 saniye boyunca 3 tanesi bekliyor. Öyle olacağını bilseydim ben baştan derdim ki ilk önce sen 4'ten bir çalışmaya başla 4 saniye boyunca. 4 bittiği zaman 3 tane elinde birlik iş olacak. Onları çalıştırırsın. İşte şu. Bu sırada çalışacak. O zaman 4.4'e geliyor. Bu bilgi varsa elinde kullanabilirim yani bu short spot şeyi. Okay, so this is the last batch system scheduling algorithm. Shortest remaining time next. Okay, so in order to maximize our turnaround time, okay, maybe we should introduce preemption back into the batch systems. Maybe we should introduce preemption into the batch systems. If I do first come first served with preemption, okay, I can do the shortest remaining time next. If I am running a job, okay, if I am running a job, and while I am running it, a new job arrives. If I preempt the running job, if the new coming job is shorter, okay, and let the new job run, then I can maybe improve my turnaround time. Okay, still need to know run times in advance. Okay, and it will help short jobs get good service. And but sometimes if I have a very large job waiting in the queue to be executed, it might get delayed all the time because shorter jobs will take the priority all the time because this is doing the shortest remaining time next. So I will do the preemption. Preemption is bad for the CPU utilization, but it might be good for the turnaround time optimization. Because this one say that when let's say I have 3 processes, process A, process B, and process C. This one will take 4 seconds, this one will take 1 second, and this one will take 1 second. But this one will take, okay, these are the durations. These are the arrival times. This will arrive at time 0. This will arrive at time 2 and 2. Okay. So in this case, job A will start running. Okay. In time 2 seconds, at time 2 seconds, job B and C will arrive. The shortest time remaining next will stop job A from using the CPU. It will immediately start running B. Then after that, it will start running C. Then after that, it will continue running A again. Okay. So this will optimize my turnaround time because it is letting B and C complete before A is complete. Yes.
Diğerine göre farkı sadece bunun kesmesi mi? İşlemi kesebilmesi mi?
Kesmesi ama eğer şimdi bu durumda ne? A 2 saniye çalışmış, 2 saniyesi daha var değil mi?
Aynen.
B ile C'ye gelmişler, onların birer saniyesi var. A'nın arta kalan 2 saniye, 2 saniye 1 saniyeden daha fazla olduğu için öbürlerine çalışmasını izin veriyor. Sadece farklı kesmesi değil yani. Remaining time'a da bakıyor. Arta kalan zamanı. Eğer şunlar 3'te gelseler de tamam mı? O zaman
Hepsi
A
eşit
çalışmaya
olacak.
devam edecek. Çünkü remaining time'lar aynı. Tamam mı? A çalışmaya devam edecek. Remaining time'a bakmam lazım. Şimdi bir prosesi ortada kesebilmek için timer olması lazım ya da prosesin kendisinin bloklanması lazım. Timer'da bizim batch sisteminde çok kullanmıyorduk. Eğer turnaround time'ı maximize etmek istiyorsam ben o zaman preemption'ı kullanabilirim. So shortest remaining time next. Follow this set of rules. Again, this is correct. This is preemptive variant of the okay. First come first served. Okay, any other questions? Let's move on then. Okay, these were the batch processing computer operating systems. Let's look at some interactive systems. We had only 3 algorithms listed for the batch processing systems. How about the interactive systems? These are the types of scheduling algorithms for the interactive systems. Round robin scheduling, prior to scheduling, multiple queues, shortest process next, similar to the shortest remaining time. Okay, guaranteed scheduling, lottery scheduling, and fair share scheduling. We will check each of them one by one. Okay, let's look at this round robin scheduling. Okay, in round robin scheduling, I have this list of runnable processes. Okay, in a queue. Okay, in a circular queue maybe. The process B is running here. Okay, and next process is just connected to it. When process B is blocked or even if it is not blocked, when time is up, when there is a timer interrupt occurs, then I will start running next process F. Okay. So process B uses CPU using certain amount of time defined by this quantum value. Each process is assigned a quantum time. Okay, quantum is a time value. I cannot use my CPU more than this time. Okay, let's look at that actually. Okay, this algorithm is one of the oldest, simplest, fairest, and most widely used algorithms in the operating system history. It's called round robin. Round robin'in Türkçesi neydi? Dönme dolap. Dönme dolap gibi. Dönme dolap ne biliyor musunuz? Dolapla alakası yok dönme dolap. Dönme dolapta ne var? Düşünün. Dönme dolabın en yüksekte olduğu durumu düşünün. Herkes en yüksekte olduğu durumda CPU kullanıyormuş gibi düşünün. Kimse yapamıyor. Belli bir zamandan daha fazla en yüksek durumda kalamıyor. Diğerleri sürekli olarak gelmesi lazım değil mi? Sürekli yani bittiği zaman tekrar başlıyorsunuz. So this is one of the oldest, simplest and fairest. Each process is assigned a time interval, and that time interval is called quantum. And during that quantum time, you are allowed to use the CPU. Okay. If the process is blocked before using the whole quantum time, then you can do the switching. If the process is still running at the end of the quantum, the CPU is preempted and given to another process. How the CPU is preempted? Because you are using a time interval. Okay. Without the hardware help, I cannot do preemption. Okay. I cannot do multitasking, preemptive multitasking without the hardware help. But without the hardware help, I can do multitasking if I use non-preemptive systems. If the process has blocked or finished before the quantum has elapsed, CPU switching is done when the process blocks. Okay, so there is two things. If my time is up, if I use the whole quantum and I'm still running, my process will be preempted, okay? And before my time is up, if I am blocked due to some system code, my process will be switched again. So there are two ways of switching from your process to another process. So this is called round-robin scheduling, and quantum is the important criteria in this one. How do you make a decision for your quantum? So should the quantums be large or small? Let's say I have a quantum time of 100 milliseconds. Should I make it 100 milliseconds for each process, or 500 milliseconds? Or maybe 10 milliseconds? How do I make the decision? Smaller quantum times means that, what does it mean?
More switches.
More switches. But more switches is not, we don't like switching actually, right? Switching is bad in terms of CPU utilization. Because when you do the switch, you waste 10% of your CPU time if you do the switching too often, okay? But if I don't do the switch, then I will lose my interactivity, okay? I want to be interactive. When the user clicks on the screen, okay, when the user does this, he wants to see some kind of an effect on the screen. I should keep my interactivity all the time, but to keep interactivity, if I keep my quantum time smaller, then I will start wasting my CPU time. I will start wasting my CPU time. I cannot run many processes at the same time because I am using most of my time in switching from one process to another process. Here is some analysis directly from the book. Okay, the shorter the quantum, the more responsive the system. This is the rule. Quantum, if it is 10 milliseconds, then my system will stay more responsive. However, process switching is expensive. Why is it expensive? Because I need to save and reload the registers. Okay, we didn't talk about virtual memory yet, but it is very expensive to switch from one virtual memory map to another virtual memory map. And the cache, system cache, CPU cache, they all have to be flushed, and lots of bookkeeping, etc. Okay, so the switching is expensive. If you keep your quantum smaller, it is good for the responsiveness, but it will be bad for the CPU utilization. Suppose suppose our quantum is 4 milliseconds. Okay, I choose it as the 4 milliseconds, and the process switches will take 1 millisecond. That means that out of 5 milliseconds, 20% of the CPU time will be used for process switching, okay, context switching. That's too much, okay, that is too much. But if we have, let's say we have 100 milliseconds quanta, that means 25 times more than this one, okay, 20 times more than this one. What will be the overhead? What is the overhead in this case? In this case, the overhead will be 20%. That's too much. If I have my quanta set to 100 milliseconds, what will be the overhead? Calculate the overhead here. How did I calculate this one, 20%? How do I calculate this one? This one calculated like this, okay? 4 milliseconds of process run, okay? And 1 milliseconds for the switch. Then 4 milliseconds, okay? 4 milliseconds run and 1 millisecond switch. It goes like that. So out of these 5, this 20% is wasted, right? How about this one? I have my 100 milliseconds quanta, and I will waste, after 100 milliseconds, I will waste 1 millisecond for the switching. So that means that I have less than 1% overhead. Instead of 20% overhead, I have less than 1% overhead. So larger the quanta, better the CPU utilization. But if I have 100 millisecond quanta, and if I have, let's say, 20 processes running on my system, interactive processes running on my system, if I have 20 of them, that means that it might take 2 seconds for some of the processes to get the CPU time, right? Because I have 20 of them, it might get 2 seconds for some interactive processes to get the CPU time, and my interactivity will get hurt, because when I do this, it will take 2 seconds to see the effect. But when I do this, I am immediately seeing that I can do it. Okay. So if the queue gets long, okay, even cheap request. What's a cheap request? What's a cheap request? We talked about this yesterday. Cheap request. Even cheap requests will take too long, and we need to make a reasonable compromise. Maybe 20 to 50 seconds like this. Okay. What's a cheap request? We saw this yesterday, cheap request and expensive request.
It may not be cheap, but in a viewpoint of a person,
Yes. In a viewpoint of
cheap
a person,
requests must be met immediately.
immediately. So it may not be cheap in terms of CPU utilization or CPU computer resource utilization, but the user, the computer user, operating system user, expects some task to be completed immediately, like this one. When I click on this one, I should see this. As soon as I click, I should see this. Otherwise, my expectations are not met. I would say that the system is slow. If the queue gets even long, that means that lots of processes are waiting. So your round robin is turning very, very slowly, right? Because everybody is spending 100 milliseconds at the top of the round robin. So it is turning very, very slowly. In that case, for some of the jobs, for some of the processes, it will take lots of time to reach to the top of the round robin. And even for the cheap request, it will take that many times, 2 seconds, that's a bad thing. In our case, if I am writing an operating system scheduler, process scheduler for a cell phone, okay, since CPU utilization is not a big issue for me, maybe 20% overhead is not that bad, because I am not using my CPU 100% of time. I never do this, okay? I will never, maybe rarely, I will rarely use my CPU 100% of the time on a cell phone operating system. In that case, it might be feasible to use very small quanta with this large overhead of switching, because my CPU is always available to me. And in that case, in order to be able to stay very, very interactive, I can keep my quantum at small rates. But this solution may not be very good for mainframe computer or maybe for a web server. Okay. So the quantum length is the key parameter for this round robin scheduling algorithms. Any questions? So the compromise is maybe between those 20, 50 milliseconds. Okay. Another algorithm, we are going on these algorithms one by one. Round robin scheduling, let's look at this priority scheduling. Priority scheduling, I may not have enough time for this one, but we say that not all processes are equally important. Some of them are more important. For example, a backup process is not that, well, it is important, but it doesn't have to be done in a quick, it doesn't have to be done quickly. It might wait for a while. So if we assign priorities to processes, okay, then maybe the important ones, maybe the ones that the user thinks that they are cheap, the cheaper ones will get higher priority, the other ones will get lower priority, and the higher priority processes will run first. Okay, the simplest version, always run the highest priority processes. Assign them priorities. Okay, how do I assign the priorities? It is not at the operating system design time. we know that backup processes should be lower priority, or the interactive processes should have higher priority, okay? So if I know the priorities of the processes, the simplest algorithm prior to scheduling algorithm would be run the highest priority processes first, okay? Then run the next level, then run the next level, and at the end, you would run the lowest priority processes, okay? This may not be a good idea though, okay? If the highest priority process is a CPU bound process, then it will never let the CPU go, okay? It will never let the CPU go because it is not blocked, it is using the CPU all the time. It cannot be preempted, even though if it is preempted, it is the highest priority process, so it takes the CPU again. So it's not a good idea to let the highest priority process run all the time, okay? So we should develop some other ways of handling this priority schedule. So what will be your solution to this problem? Suggest me a solution. So that the highest priority process takes the CPU all the time and never lets it go. How do you solve this problem?
Time step.
Time?
Time step.
Time?
Time step.
What do you mean time step?
You can assign the maximum time for each process and each
So when the time, you mean preemption?
yeah.
But when you preempt the highest priority process, how do you make a decision to run the next level? Because it is still the highest priority process and it will run it again. Yes.
Prioritisini düşürürüz.
Maybe, yes.
Geçici olarak düşürürüz.
Maybe we can, maybe if it, okay, we do the preemption. When we do the preemption, we look at the priorities, and if a high priority process is taking too much CPU time, maybe we should drop its priority to a lower level priority class. In that case, other processes will get some CPU time. Otherwise, as I said before, the highest priority process will take the CPU all the time. So this is one solution. There might be other solutions, and we will see those. Remember this priority. There is this priority inversion problem. We talked about this already. We are revisiting it again. Let's say the priority of this process H is higher than priority of this process M, and priority of this process L. And if the process L holds a lock, okay, and this process H needs that lock, H needs a lock held by L, so H blocks, okay. When H blocks, it cannot continue, right? H blocks. Then the scheduler will let this process run, process M will run, because M has a higher priority than L, okay? M that was already on the list gets the processor before L. So that means that H indirectly waits for M. Even though the priority of H is higher than M, okay, it has to wait for M to finish its job. Okay, so this is called priority inversion again. The last time that I showed you this one, it was at a different context, but it was again called priority inversion. So we have this problem for real systems actually, and this is one example for a spacecraft pathfinder. We had this problem of priority inversion. The book has the details. Okay, that's it for today. On Monday at
5.
What is Monday? Monday is 27th, okay? So March 27th at 17:00 we have our midterm exam. Okay, it will be 2-hour exam, and it will be in this classroom and Z23. Any questions?
Buraya kadar.
Buraya kadar.
So this is yes, it is up to this point. You're right. including this whatever. Okay, so on Monday I might do 2 hours of lecturing. I am not sure. Maybe Mohammed can do it too. I am not sure, but whatever I will cover on Monday, it will not be included in the exam. Okay? So the exam is up to this point. Okay, any questions? Okay, study hard. Çocuklar, imza atmayan var mı?